So up to this point, we've talked about the atom, the different subatomic particles of the atom, and how the atom is constructed. In this chapter, I want to go into how two or more atoms are brought together and how compounds and molecules are constructed. The atoms and compounds are held together by attractive forces called chemical bonds. There are two main types of chemical bonds, ionic and covalent. Ionic bonds do not share electrons, but form bonds through electrostatic attraction of positive and negative ions. Covalent bonds do indeed share electrons. To understand ionic bonds, we need to know why atoms form ions. The best way to describe this is through what is called the Octet rule. In 1916, Gilbert Lewis pointed out the lack of reactivity in the noble gases of group 8A, indicating a high degree of stability in their electron configuration. Helium, with its filled valence electrons of 2 electrons, one s2, which would be right here in group 8A. You can see going back to the electron configuration, this would be 1s, it has 2 electrons in the orbital. Neon with a filled valence shell of 8 electrons, and it has a filled valence electron shell of 8 electrons right here. And argon with a valence shell of 8 electrons, 3s2 and 3p6, and so forth as we go down the group. So in this column right here, all the valence electrons are filled. Very quickly, I want to go over some characteristics of the noble gas group, or the column 8A, with some things that we already know. We had mentioned that period 1 has 1 shell, period 2 has 2 shells, period 3 has 3 shells. And using the Bohr model, we'll start with helium. It only has 1 shell, so it would have 2 valence electrons. So this is completely filled, and we can find that with the electron configuration and the box arrows right here. We can see the electron configuration right here. Moving down to neon. Neon would be in the second period, so it would have 2 shells, and it has a filled valence shell. This has 8 valence electrons. There's 8 electrons in this outer shell, which would be filled. And looking at argon right here, this is the third period, so it would have 3 shells. So in the outermost valence electron orbit would be this ring or orbit. And essentially what the Lewis dot structure is doing is, instead of writing all this down or all this down, we just simply write the element abbreviation, like for argon, and there are 8 valence electrons. Because it's in column 8, it would be 8A. We just put 8 dots around it, and it's done. So let's get back to the periodic table. Pay attention to the A groups. We have 1A, 2A, so on. Notice that this portion of the periodic table is labeled with column B. We will not use this for what we were talking about. What we want to pay attention to is the main group elements, which would be this area and this area. So if we took periodic table and collapsed it down to the main group elements, we would have something that looked like this, where it had 1A through 8A. And we can see how the Lewis dot makes very quick work of what we just went over. Hydrogen would have 1 valence electron, helium has 2 valence electrons, neon and argon have 8 valence electrons because they're all in groups 1A. Groups 2A has 2 valence electrons, 3A has 3 valence electrons, 4A, and so on. So to wrap this up, we know that valence shells are the outermost incomplete shell. A valence electron is an electron in the valence shell. The symbol of an element represents a filled shell or filled shells. The number of valence electrons is the same number as the group number. Before we get into the nuts and bolts about the octet rule, I wanted to define what an ion is. Before we see as we go across the periodic table, the number of protons and electrons are added equally. Hydrogen would have 1 proton and 1 electron, helium would have 2 protons and 2 electrons, lithium would have 3 protons and 3 electrons, and so forth. When an ion is formed, this is no longer the case, and there's an unequal number of protons and electrons. Atoms and their ions are nothing alike chemically or physically, making them entirely different species. Here we have a lithium atom with 3 electrons and 3 protons, and here we have a lithium ion with 2 electrons and 3 protons. So the protons and electrons would not be the same or not equal. Here's a fluorine atom with 7 protons and 7 electrons, and this would be a fluoride ion with 7 protons and 8 electrons. So the protons and electrons would not have the same number of subatomic particles. So the number of protons and electrons would no longer be at a 1-to-1 ratio. The octet rule says there's a tendency for elements in groups 1A through 7A to react in such a way that achieves an electron configuration of 8 valence electrons. So looking at 1A, and we went down to lithium, and group 7A, we have fluorine. The best way for lithium to reach a full valence electron configuration where the outer shell is filled would be to lose an electron, and fluorine would assume a filled valence electron configuration of 8 valence electrons by gaining an electron. A metal atom that loses 1 or more electrons becomes a positively charged ion called a cation. A nonmetal atom that gains 1 or more electrons to become a negatively charged ion is called an anion. I want to take our table and break it up to illustrate an idea of what is happening. Looking at the lithium would have 2 shells, and it has 1 valence electron on the outermost shell, so it would lose an electron to reach the noble gas configuration of helium, and fluorine gain an electron to reach the noble gas configuration of neon. So metals will lose electrons to become cations, and nonmetals will gain electrons to become anions. Here's a more detailed table just for completeness sake to illustrate what ions would be formed. So going down to the third row, we would have sodium. It would form a charge of 1. Magnesium would form a charge of 2. And in the third column, aluminum would form a charge of 3. Moving over to the nonmetals, fluorine would form a charge of -1, oxygen would form a charge of -2, and nitrogen would form a charge of -3. Let's take a look at what's going on here. If we pick group 1A and we select sodium, sodium has 11 positively charged protons and 11 negatively charged electrons to give a net charge of 0. Writing the electron configuration, we could write, or we could write the Lewis dots. So the sodium ion is then wrote as, it still has the same amount of protons, which would be 11. Metals lose electrons, so it would now have 10, and that would give us a charge of 1 and give us an electron configuration of this. So moving over to the nonmetals, we could choose group 7A, say chlorine, and chlorine has 17 protons and 17 electrons to give it a net charge of 0, and the electron configuration would look like this. Drawn a Lewis dot structure, would have a outer valence electron shell just shy of a full octet. Chlorine atom would then gain an electron to bring it into a full octet of the noble gas. So that would give us a total of 18 electrons. So the electrons would equal 18 and the protons would equal 17, leaving us a charge of -1. So chlorine would have a charge of -1 and sodium would have a charge of 1. At this point, I would like to illustrate how an ionic bond is formed. So we have a metal and a nonmetal. We know that metals lose electrons to form a cation, and nonmetals gain electrons to form an anion. So you can kind of guess what happens here. The 1 valence electron on the metal goes to the nonmetal, and we have the metal cation and the nonmetal anion with the 8 electrons in the valence shell. And through this, there's an electrostatic attraction. One thing I do want to point out is there is no sharing between an ionic bond. It's a complete transfer of the electron from the orbital of the metal to the orbital of the nonmetal. When writing formulas for ionic compounds, the total number of positive charges must equal the number of negative charges. And so far, we had sodium chloride, which is a 1-to-1 ratio. But obviously, all ionic compounds aren't 1-to-1 ratios. So let's split this down the center. And if we wanted to go to group 3, where it has a cation of 3, just put 3 here. And we went to group 7, where it has an anion of 1. This has to match somehow. And we can do that by adding 2 more ionic species to where it finally balances out. So we would have 3 different ionic species of -1 to total 3. A quick and dirty way of doing this when writing ionic formulas is the crisscross method. So for example, if we had barium, which has a positive charge of 2, and iodide, which has a -1 charge, we would just crisscross these like this and rewrite the compound like this. The subscripts represent the number of atoms in the compound. So iodine had a negative charge of 1, so it would come down to barium. We could put 1 there. Barium had a positive charge of 2, so we could put 2 on the iodine. And by convention, if subscript is 1, we just leave it out. So we could just write barium iodide as the formula. Another example would be if we went to the 3rd group with aluminum, where it has a positive charge of 3, and we went to the 6th group with a sulfide ion with a negative charge of 2. We could simply crisscross the charges, so it would be aluminum, then put 2, and then S for sulfur, put the positive charge of 3 on the aluminum as a subscript on sulfur, subscript of 3. And this would then give us aluminum sulfide. And these are what is called monoatomic. When there's ions of more than 1 atom, it's called a polyatomic. Poly meaning more than 1, mono meaning 1. So let's look at some polyatomic ionic compounds. So we have the sodium ion and the bicarbonate ion, and these are a 1-to-1 ratio, cancel out very nicely. So it would just be written like this. And I'll show you a polyatomic ion that is not a 1-to-1 ratio, just to show you how the crisscross method would work with that too. One is potassium, the positive charge, and the phosphate ion that has a -3 charge. And then we would just crisscross the charges. So that would become K3PO4, which is potassium phosphate.